What I'm going to talk to you about today is following on from Charudata's really nice presentation on imaging with electrons. We're going to have a look at what we can do with X-rays instead, so as a complement. I'm going to show you a little bit about what is possible now with the state of the art. I'm going to try and squeeze in some new results, so apologies to the chairperson if I run over time. Yeah, I think there's a lot of possibilities now to look forward to in the next wee while. But first of all, what I'd like to do, if it's possible, is start off with the most important slide of the talk, which is, of course, a massive thank you, first of all, to my group in Dresden, funding agencies, but most of all, to all of my collaborators around Europe and the world, without whom this would really not have been possible. We do a lot of this large-scale facility work, and these collaborations are really key and really a lot of fun. So we're going to start off, and we're talking about imaging with X-rays of three-dimensional spin textures. And we've already heard some wonderful talks earlier today about what kind of spin textures we can get. And so what I want to really identify here is that we kind of have two main regimes of 3D spin textures, I would say. We first of all can consider spin textures in extended space. So by thinking about going to the third dimension simply by extending from a planar film into the bulk. And there we can have, for example, the presence of these Bloch point singularities forming topological transformations, the formation of chirobobbers and torons, which of course also include Bloch points, and of course these Hopfion-like textures that were nicely introduced by Philip earlier. But we can also consider looking at 3D confined spaces, as we heard more about yesterday, where really now by patterning our magnetic material in 3 dimensions, we can now achieve Bloch points in cylindrical nanowires, or indeed by patterning artificial chirality into a structure, achieve spin helices in a non-chiral and achiral material. And so essentially what we need in order to be able to image these systems is the combination of being able to resolve things in 3D space and also resolve the magnetization vector, the 3-dimensional vector orientation. Now, when we think about this, what we turn to basically is tomography or 3D imaging. And there are 3 key ingredients of tomography, I would say. The first of all, the basic ingredient is measuring 2D projections of M or B. So for the X-rays, we're measuring M, the magnetization. We then need to measure all 3 components of M by making sure that we measure these projections for many different orientations. And then we develop reconstruction algorithms in order to recover these 3-dimensional vector fields. Now, this can be done with a number of different probes. So we've already seen very nice results in the previous talk that with electrons we can do high spatial resolution imaging of B. May not all be aware that this is also possible with neutrons, however on much larger scales, so not so relevant to our nanomagnetism. And of course, we also have the case of X-rays, where again, we're probing directly M. And it's the X-rays that I'm going to be talking to you about in this talk. So what I'm going to first of all do is give you a quick reminder of, or an introduction as to what we can really achieve with X-rays by showing kind of our first result of X-ray tomography, which was already published a good few years ago now, during my PhD with Laura in Switzerland. So the idea here was that we took a gadolinium cobalt pillar, which we cut from a nugget. Key thing to consider here is that it's 5 micrometers in diameter. So with X-rays, we can really image much thicker samples that are possible with electrons. And by performing hard X-ray magnetic tomography, we were then able to recover the internal magnetic configuration of this chunk of material with about 100 nanometer spatial resolution. So in this way, you can see that the magnetization, we can really recover the vector in 3D space. And in this way, we got an insight into, for example, the kind of 2-dimensional topological textures we found, so vortices, anti-vortices, and how they, let's say, propagate through the 3-dimensional space. But we were also able to, for the first time, directly image these magnetization singularities in 3D, these Bloch points, which, of course, mediate topological transformations in 3D. And it's quite funny, actually. I really appreciated Kai's mention of the workshop in 2016 that Peter hosted already now, 8 years ago, where I think we were showing the first results of X-ray magnetic tomography. And actually, when I was contemplating or reflecting back on this, you can really see how far we've come, because if we think about today, where we can do X-ray magnetic tomography, where it's been implemented, it's already been implemented at 6 different synchrotrons around the world, which I find quite exciting or quite remarkable. But more than that, it's already in development at 3 further synchrotrons. So we're reaching the big 10. And we've already got a dedicated beamline at Diamond 2, which is going to be pioneered by David over there, really dedicated towards this 3D soft X-ray imaging. So you can say that since, let's say, our first paper 7 years ago, it's really come a long way, and I think there's even more opportunities, I think, for the next few years. So, okay, we have so far, what I want to start off, first of all, in the first half of my talk or so, is talking about where we are so far with our capabilities of X-ray 3D imaging. And there's going to be 3 aspects. First of all, I'm going to look at magnetic textures in extended systems, which relates to the talks that we've heard this morning. Secondly, we're going to look quickly at some 3D configurations of 3D nanomagnets relating to what we saw yesterday. And lastly, we're going to touch on how we can go to dynamics. So actually image megahertz and gigahertz dynamics in 3 dimensions. So let's start off with our magnetic textures in extended systems. And as we've already heard a lot today, I'm not sure I need to introduce this again, but let's say topology is key when we're looking at interpreting the magnetic configurations of our 3D textures, right? And so what we can do, we know all this well, this is the skyrmion number, the integral of the to give the skyrmion number. What we can do is that we can take actually what's inside the skyrmion number integral and actually calculate this as a vector. This is known as the magnetic vorticity. Now, with our 3D data that we get from our X-ray magnetic tomography, we can directly calculate this property, which directly relates to the topology of our system. And with that, what we can do is we can, first of all, map 3D networks of topological textures. So you see now within this bulk of this 5 micrometer wide ferrimagnet, we have the cores of vortices and anti-vortices. But we can go further, and we can actually plot regions where we have an abrupt change in our topology, i.e. the presence of these Bloch point singularities. And indeed, where we have a sink or a source of our vorticity vector, we'll have a Bloch point or an anti-Bloch point texture. Now, as well as, let's say, mapping out different types of magnetic configurations in 3D with this technique, it also allows us to identify different types of 3D textures that we have observed in these systems. And first of all, one particular texture that we've been able to observe were these magnetic vortex rings that were not formed of skyrmions, but of vortices and anti-vortices. Now, what's particularly nice here is that because we have our vector field, we can directly apply some of these analysis techniques that were mentioned earlier. For example, we can calculate these pre-images that are key to determining the Hopf index or the linking of your texture. Now, for this particular case, you can see that the pre-images do not link, so we do not have a Hopfion. But what I think this is really nice is that it shows us that if we did have a Hopfion, we would have the possibility to really prove in 3D that it has the correct topology. Secondly, we were also able to identify a different type of texture, which are these magnetic torons. Here you have basically in the plane the equivalent of a skyrmion. You have a Bloch point and anti-Bloch point at the top and the bottom. And essentially, well, this was already very nice to see in our configuration, but why is this particularly motivating? Well, they've been already observed alongside Hopfions in liquid crystals, as well as in ferromagnetic micromagnetic simulations. So I think the fact that we can, first of all, observe these and actually identify them with these kind of techniques really gives us quite a lot of confidence that we will be able to identify these Hopfion textures in the future. Okay, so that's our talking about 3D magnetic textures in extended systems. Now let's go from 5 micrometers in size down to about 100 nanometers or below and look at these magnetic double helices that I worked on when I was working with Amalio when I was in Cambridge before moving to Dresden. And these double helices are specifically interesting because they are separated in space. So we have let's say, the curvature and the torsion of the helical nanowires, but they are strongly dipolar coupled. Now we can grow these with FEBID, as was introduced yesterday by Amalio, and you see that we have this separation of the 2 nanowires that you can see in the SEM image. But we go to the X-rays, we can actually see with XMCD imaging that we can actually resolve these helices, and the black and the white essentially indicates the orientation of the helix. So in the ground state, in the as-grown state, we have anti-parallel alignment, when we can apply strong magnetic fields perpendicular to the long axis and nucleate basically a regular array of domain walls. Now, if we want to work out what the effect of the three-dimensional structure on these domain walls is, we can apply, of course, or perform 3D magnetic imaging, this time with soft X-rays, and we can actually resolve our three-dimensional magnetic texture in these double helix, these nanostructures. Now, what you can see here is quite interestingly, compared to the direction of the field that was used to nucleate the domain walls, the domains generally point the same way, but the domain walls point the opposite way. And this is because they reverse due to strong dipolar coupling. Now, what is particularly interesting is when we perform micromagnetic simulations, we see indications of something non-trivial happening in the stray field surrounding these domain walls. So we can have a look, and indeed, surrounding the domain walls, we see these topological anti-vortex textures. Is maybe what we should be looking at with electrons with the Charadata. Why this is particularly interesting is that it gives us the idea that with these 3D nanostructures, we can potentially pattern textures into our magnetic induction. Now, this hasn't been so explored yet, but I think this would be a very interesting thing to consider in the next few years. Okay, and lastly, let's say in terms of our state of the art, we want to talk a little bit about our capabilities for imaging going to the fourth dimension in X-ray 3D imaging. And in particular, what we take advantage here is we have actually developed a slightly alternative imaging geometry, which means that we can actually combine our 3D imaging capabilities with pump probe. So for those of you who are not aware, the synchrotron X-rays come in pulses of about between 50 and 100 picoseconds in width at 500 megahertz. And this allows us essentially to do time-resolved imaging, which is very, very standard when it comes to 2D XMCD imaging. Well, we can combine this with basically our 3D imaging to get an insight into the dynamics of our 3D configurations. But let's first of all have a look at what our magnetic configuration is. We performed a static configuration, and we see in this disk that we have kind of in the top part of a disk stronger anisotropy. It's pretty much single domain. But in the lower half of the disk, we have these two vortices because we have lower anisotropy. This is a nice test structure to be able to image or to test whether we can image the dynamics in 3D. So we go on to do this, and what we can first of all see is if we look at these vortices in the lower half of the structure, I'm not sure if people at the back can see this, but we have this dark point gyrating from side to side of the bright reference point. And so essentially we demonstrate we can track the motion of these vortices within the bulk of our 3D structure, which in principle could also be applied to skyrmions, one-day hopfions maybe, or the like. But we can also map out, let's say, do some Fourier analysis of our data and also map out coherent rotation modes in our data set. So being able to basically pick out where we have strong oscillations or gyrations of the magnetization and allowing us to map out potentially spin waves. Now, one key limitation, let's say, with this particular technique was that we were limited to the 500 megahertz of the synchrotron. And I think everyone will be aware that that's not quite good enough if we really want to look at resonant magnetization dynamics. So we went on and implemented this with a slightly alternative imaging technique, which is time-resolved scanning transition X-ray microscopy. It essentially has a faster detector, so we can really vary the excitation and the frequency at which we're imaging our dynamics. And let's say in a nice demo again, we were able to show that we could measure the resonant dynamics of this Landau pattern, tuning to the 300 megahertz resonance of the vortex core, and then the 900 megahertz resonance of these domain walls. And so again, just like we were saying about the topological textures, this potentially opens up the imaging of resonant dynamics in 3D for many of your samples. Now, a quick demo of how we have used this actually for our for a real life scientific case. We've recently had the pleasure to work with David Girardi, Edoardo Albisetti, and Daniela Petti from Milan, who work, of course, on spin waves in synthetic antiferromagnets. And essentially what we did is we took their sample, again did this time-resolved laminography, and we have in their sample, again, a Landau pattern, but here the domain walls are emitting spin waves in the system. Now, what we could actually do is perform the 3D imaging and we can really see in 3D, get information as to the three-dimensional structure of these spin waves. So for example, we could see how the spin wave modes are localized in 3 dimensions. And we could also look at regions where we have interference of spin wave modes and map out this kind of non-trivial 3-dimensional texture or structure. And I don't have time to dwell on this, but more than happy to answer questions, or we recently got the paper published a couple of weeks ago, so I would check that one out. Okay, so I hope everyone's all right so far. That's me so far, giving you a little bit of an idea of where we are with our state-of-the-art. So essentially to repeat myself, or just to summarize, we have the possibility to image static configuration in extended systems, in nanostructures, and also to go towards their dynamics. So if any of you think that this could be potentially interesting for your systems, it would be more than happy to chat. But what I want to do with the rest of the talk is talk about some challenges that we've identified and tried our best to address in the last few years. And the challenge particular that I want to talk about is this idea of imaging a wider range of systems. In particular, looking at these thick magnetic systems, which actually we had huge limitations up until now. I'll explain that in a second. And going beyond ferromagnets towards other types of ordering, for example, in orientations towards antiferromagnetic tomography. But let's start off with looking at thick magnetic systems. And if we think about, I mean, we've already heard a lot about Hopfions today, but just to give you a quick overview or reminder where we are, we have already a large number of theoretical works telling us about how we could potentially expect to see these Hopfions or look at their dynamics and behaviors. And we've got some first really nice experimental observations indicating where and how we might be able to find these textures. But we don't yet have 3D imaging of a Hopfion. And the question may be, well, why? Well, it turns out there is an actual challenge because we need to find the right material, the right geometry, and we need to be able to actually look at this with our imaging capabilities. So let's think about what our imaging capabilities are. What are our limitations at the moment? Well, we need, as I said, to target different materials. And essentially what we need, I would say, is we need to have flexibility in the space, so in the geometry, how large our samples can be. We need to be able to look at different materials, of course, and we need our high spatial resolution. Now, we have two different, I would say, sets of probes for this. First of all, we have our hard X-ray imaging, where we have loads of space, right? We've shown you that we can look at 5 micrometers worth of material. However, this major limitation here is that we can only probe rare earths. So when it comes to transition metals, we really struggle. And to give you an idea of the challenge that we have an iron gadolinium multi-layer, very strong contrast at the gadolinium edge, but at the iron edge, we basically, if you squint, you can see the stripes, but this is essentially too noisy for us to really be able to do the 3D imaging. On the other hand, we have with our soft X-rays and our electrons, as we heard in the previous talk, the possibility to look at different materials and with high spatial resolution. However, there, you're limited to thinner samples, so on the order of a few hundred nanometers. And so the main challenge is, how do we combine all 3 of these capabilities in order to be able to hopefully find and image these Hopfion textures? Well, the answer comes actually with coherent imaging techniques. And these coherent imaging techniques I'm not going to go into too much detail about, but the key thing is that we are able to recover the full complex transmission function of our sample. Now, what this means, well, let's think a little bit about what we're doing when we're actually measuring XMCD. We have our absorption spectrum here in black, and you'd see the red line here is our XMCD spectrum. And the reason why that we're limited to thin samples is because our XMCD essentially coincides with the peak of absorption, meaning that if we want to measure magnetic contrast, we need to measure, or we're limited to thin samples. However, we have access now with the coherent imaging to the full complex transmission function, which means also the phase contrast. And now you can see across our absorption spectrum, we have this blue spectrum, which is our phase. You can see it exists almost at all energies, right into this pre-edge where we have much less absorption. And what this implies is that we potentially have the possibility to measure now with this phase contrast these strong XMCD signals, but for much thicker systems. So we can go on to try this. And of course, we didn't start off with, let's say, already applied samples. We started off with some perpendicular anisotropy multi-layers, iron gadolinium, of varying thicknesses going from about 100 nanometers up to 2 micrometers almost, where you can see for the 1700 nanometer thick sample, it basically saturates. We get almost no transmission except in the pre-edge. And if we have a look now at our amplitude and phase XMCD, as we go up in terms of thickness, the amplitude, we soon lose our quantitativeness, but actually with our phase imaging, we retain this quantitative equal and opposite XMCD signal up to almost 2 micrometers in thickness. And this really means, or it really allows us to overcome this key challenge of imaging thick systems based on transition metals. Now, we've already tried to apply this new capability to systems that have so far been inaccessible, and I want to give you a couple of examples. The first one is in micrometer thick Healy magnets. And I think in Philip's talk, he gave this very nice example of how in the Hopfion, let's say as you go from, what was it, 100 nanometers up to 800 nanometers, you have, let's say, it would be good to be able to compare and measure these different thicknesses, right? But up until now, because these typically don't have our nice gadolinium, or they don't all have gadolinium that gives us our strong XMCD contrast, it's not been possible to image. So we went on and we patterned almost 1 micrometer thick chunks of cobalt zinc manganese, a room temperature Healy magnet. And it turned out that by looking at the XMCD signal in the pre-edge, we were able to get this strong XMCD contrast. And you can see already an indication of what's going on in terms of our confinement. Because in this region, which is about 400 nanometers thick, we have strong confinement effects. Our helices basically are strongly ordered. But in this less confined region, which is about 1.3 micrometers thick, the contrast is very non-uniform. And essentially this indicates that we have some more complicated 3D configuration. Of course, I'm not saying we have a Hopfion there, but what it does, it already gives an insight into we can now image such systems if we go to 3D, and we have an idea of maybe where the threshold lies in terms of strong confinement effects for these materials. The second example that I want to give very quickly is actually a completely different system that I'm not sure is really on the radar of people in this room, but it's actually naturally occurring magnetite samples. And so these are typically magnetofossils or samples that are taken from meteorites, for example. And up until now, these magnetite samples typically have needed to be cut up in order to image their magnetic state, which, as we know, will dramatically change the configuration. But again, by going to this pre-edge, we're able to, for the first time, see the magnetic configuration in a non-destructive way, giving it, let's say, maybe not us, but our colleagues who work in that community, the first, let's say, tool to be able to study their samples. Okay, I think I have like a couple of minutes left, so I only have a few more slides. But in the last couple of minutes, I want to tell you about this last work that we've been doing over the last few years with a student, Andreas Apsteros, who's hosted by Laura in her group. And the idea here is going beyond ferromagnets to linear dichroism. So let's just catch up quickly and think about, so far, what I've been showing you is actually work based on circular dichroism, where we probe the magnetization of our sample. And indeed, in this way, we can image these vector fields, these ferromagnetic textures in XMCD. We have beautiful results imaging these block points. However, we also have a different type of dichroism with X-rays available to us that gives us access to orientation fields. And of course, we're very familiar with the orientation fields of antiferromagnets, the Nail vector. We're also familiar with orientation mapping of crystals, but there's many, many other types of materials that can benefit from such imaging capabilities. And so what we've been doing over the last few years is trying to develop these capabilities to image these orientation fields in 3D. Now, I'm not going to show you antiferromagnets, unfortunately, but what we have been working on is the imaging with the same principle of crystallographic grains in 3D. And in particular, we looked at this catalyst of vanadium oxide, which is already of use, is widely used industrially. And the idea is, again, we perform essentially linear dichroism tomography, which is exactly the same idea. We have these projections, which we measure with different polarizations of light. We measure this for many different orientations of our sample with respect to the beam. Here you can have an idea of what our contrast looks like. And in this way, with the new reconstruction algorithms that we were able to develop, we can recover the orientation in 3D. Now, to give you an idea of what we have, we can first of all look at the electron density. We see already in our sample, we have a number of kind of grain-like things that we can see. But it's not until we look at the crystal orientation tomography that we see that we have a huge amount of information demonstrating that this technique really has the capability to image complex orientation configurations across, again, micrometers worth of material. We can use, of course, this orientation to segment and to identify grains that cannot otherwise be identified. And in addition, let's say we can look at specific examples of different configurations. So, for example, we can identify, let's say, single crystal grains that already from the electron density looked like they were single crystal. So this was no real surprise. But we can also look at regions where in the electron density you cannot discern any grain boundary or anything at all, but the orientation allows us to identify very clearly grain boundaries, which would be the equivalent of antiferromagnetic domain walls, for example. We also, surprisingly, and I'm not going to go into this, see a number of topological defects in our crystallographic orientation. So these are these comet and tree fall defects, and we are even able to look at this in 3D, and we see again this creation and annihilation of defects as we go through the thickness. So there's a lot of nice analogies with our magnetic configurations. But I think with that, so let's say to conclude on this, this is a very nice, I think, demo of what we can do with orientation tomography. But what is really exciting is that the same principle, I hope we will have some results soon that I'll be able to show you, can be applied to pretty much any material that exhibits linear dichroism. So antiferromagnets, potentially multiferroics, and I think this is also something that would be really interesting to start thinking about in the world of 3D. Okay, so that's me. I think I'm not too far over time, hopefully. I've showed you a bit today about our state-of-the-art in terms of capabilities, so we can image 3D magnetic configurations and their dynamics. We've gone and we've established a new way, or a new capability to image thick magnetic systems, including, of course, thick heliomagnetic systems that could potentially host these 3D textures. And we've now got a new capability to image 3D orientation fields. And I think we have a lot to look forward to. So we, of course, have many challenges remaining. One of these is developing this in operando 3D imaging, so going beyond just gigahertz excitations, but to in situ fields, etc. Of course, we're going to be also hunting for hopfions along with everybody. So this will be a lot of fun exploring different materials. And we have very much on our radar trying to go beyond ferromagnets to different types of systems. So thank you very much, and I'd be happy to answer any questions.